Good morning, everyone. Good morning. If anybody's got any problem with hearing, let me know, and I'll try and speak up louder, but I'm sure that the audio is doing its job here properly, and I'll try to make sure that I do mine and making sure that we're properly heard. What I'd like to do is to talk a little bit about the need for real hardware security. And in this case, we're talking about the real hard end of hardware security. That's where we actually go in and start digging into things. But digging into things on a small scale, which means that we're going to be looking at how things work with focused ion beam at that nanometer scale. But just to start, why we need things like hardware security in the first place. There are different elements to security in this. There's always the software, the firmware, and the hardware side of things. And they all contribute to making some systems secure. But not only do they all contribute to making some systems secure, any one of them being insecure can help a system to fall from that level of security. So we must make sure that every system that we have has good software, firmware, and hardware, and that any one of those elements failing can cause us a problem. Now, of course, we're going to be talking about the hardware end of things here. First of all, in the whole conference, of course, but specifically in this talk as well. So it's very much on the hardware end. And we're also aware that no matter what we do, ultimately everything could fail in security. Our task is not necessarily to make things absolutely secure. We know that we often can't do that. It's just that it's got to be sufficiently secure that it isn't worthwhile for people to try to break that security. That's a difficult judgment to make, but it's one that people have to sort of be aware of when they're trying to either secure things or to hack into things. So what I'd like to think about now is just a little bit of what actually security means in this. And there are two cases that we can think about. There's one where you have hard problems to solve in terms of hardware security, and the other is where you have hardened problems to solve. If you imagine a really complex chip, the kind of chip like a Pentium chip in a PC or something like that, or one of the chips that's driving a mobile phone, they are very, very complex. And those chips have very small geometries, a huge number of circuit elements to them, and they are very hard to deal with because of their complexity. And that way we call them hard, but they are not specifically hardened. And really, what you have to deal with there is the complexity of dealing with those systems. On the other end of things, you have chips which might be called hardened. They're specifically made secure. But in many cases, they're simpler chips. They usually don't have the same geometries, much larger geometries, and therefore easier to get to. Many fewer components on them. But they have very specific hardware security components that you have to get around, and they're made more difficult to get into. So some of you will be working on one type of product, people will be working on other types of product, and there are two different types of ways of getting into those things and dealing with them. So in this case, for us, hardened means that you have the software and the firmware are all built in there, designed to stop attacks on the system. You have lots of things from internal firewalling and such things. These are all the sorts of hardened elements that go into making that system. You have specific features such as random number generators, true random number generators in there, which are elements that are often not present in most hard chips, but are in the hardened level of chips. Many other features in there that are designed to be secure right from the beginning. And a lot of the test functions in there, such as JTAG and other things like that, have usually been either completely removed or have been made inaccessible by some means. And if we can try to sort of get into those things again, even to be made inaccessible, that would be a big advantage to someone trying to break into that system. In any case, this secure chip has been protected against various forms of attack, and it's our job in some ways to assess that protection, or in other cases to break through that protection and try to get into it. And some of the ways of doing that, you're going to be, could be using probing to get into these things, try to find out what's going into them. You're going to try to rewire the circuit, change the layout of that circuit in small ways to try to get things working again, to try to bring up new functions to get working again that may have been disabled. And you're going to be using tools such as a focused ion beam system to be able to do that. And it's all about changing that chip behavior from its original intent to get it to do what you want it to do, rather than what the designers and developers wanted it to do. And it's how to do that that's important here. So there's a probing systems you can use for that. And if you were to sort of rewire the circuit, you can do things here. So this is a rather old circuit, but focused ion beam is what we're going to be concentrating on. Is how you can put down new tracks, such as that, which was never intended there in the first place. Or you can cut tracks, such as that. That's an example of a focused ion beam workstation. So what actually is this kind of tool that we're going to be talking about today? So the first part is that it's really a kind of microscope. It can have a number of different elements to that microscope. The first thing is that it has an ion beam, which can be focused down to a small spot to give you a relatively high resolution of what you're looking at on that circuit. A typical resolution now is about 5 nanometers. So you can see down to features that are really pretty much the smallest features you can expect in any circuits. In addition, you may have an electron microscope. And in some cases, they are quite far into the sub-nanometer range. So you really can see all the features you might expect, even on some of the 7 nanometer circuits that are around today. So you've got this very, very high resolution techniques to be able to see what's going on in those circuits, either in some of the rather larger hardened circuits that we were talking about earlier, or even on the hard circuits, which have got much finer and smaller geometries than we had been used to in the past in a long way. Another thing that you may often have is an infrared microscope attached onto this thing, which allows you to do another kind of edit and change in these circuits, which is backside editing of the circuit. An infrared microscope allows you to look through the silicon substrate of an IC. That means you're looking at it from the bottom. And there are some big advantages to that as well, but there are also many disadvantages to that too, because it's a much more complex and different technique to the normal top side view from a focused ion beam system. And we'll look at why that's useful and necessary and some of the difficulties surrounding that. Another reason for using a focused ion beam is it's not only a microscope to see what's going on there, it's also our digging tool. It uses a gallium ion beam, and that gallium ion beam can focus down onto a spot, and when it hits it, it can remove that material through sputtering. So you place your beam on a spot, maybe scan over a small area, and you sputter material away. And as you sputter, you can also introduce some gases as well. And that gas that you introduce could do things like enhance certain milling of materials. So if you were to flood the area with some xenon difluoride gas, you would enhance the milling of the dielectrics within the circuit, or if you were to use iodine or chlorine gas, you would enhance the milling of aluminium metals. And there are other gases used for enhancing, or at least helping the milling of copper materials, if that's the kind of circuit you have. And you can also use gases for being able to deposit new tracks. So be it depositing something like tungsten or platinum or something like that, you can use gases which contain those elements, those materials, to deposit new tracks in your circuit. So it's a digging tool and a deposition tool, as well as the microscope that it is. And you can use that deposition to add new circuit tracks, or new points, such as probe points, where you can get in and you can measure things on a circuit. So that's why it's a fairly versatile tool for getting into a circuit. It gives you the ability to get in there and make those changes to the behavior of that chip that allows you to make that attack and to assess its security. So let's have a look at stages in an attack. The first thing you have to decide is, what are you actually doing? Are you testing the security of the chip? Are you actually the hacker trying to breach the security of that chip for your own aims? Or are you the academic researching how that is, and that category you put yourself in determines the approach that you're going to be taking on some of these things. The next stage, you have to find out what's there. You won't be given, or at least you won't be given, any really important information about the chip, no matter who you are. So you've got to get it for yourself. You've got to be able to get some documentation, but that's not going to give you an awful lot of help. The main way you're going to be able to find out what's going on is by reverse engineering the chip. You've got to take it apart. And you've got to then, when you've done that, you've got to sort of examine what you've done and taking it apart and try to identify the weaknesses of that chip in order to exploit them. Again, it's all to do with identifying what changes you can make to the chip that allow you to take control of it. So, in reverse engineering, you can see that you've got to make a map of that chip. This is just a little cross-section of a chip that you might see, or an older one, but you've got to be able to get in to strip back that chip layer by layer. There's a number of ways of doing that. You can use wet chemical etching. You can remove some of the dielectric layers, those black dielectric layers, using materials like HF acid, hydrofluoric acid. You can remove the metals, such as the aluminium, for example, using phosphoric acid-based etches and other things. And there are other etches for copper-based materials. And you can use wet chemical etching to do that, but it's very hard because it's very difficult to get a good uniform etch on these things. I think probably more common now is the mechanical grinding and lapping, where you're polishing off these layers with a very fine slurry of usually diamond to be able to remove those materials, and you come down layer by layer, exposing the different layers as you go through it. And another way of being able to do that is to use reactive ion etching, plasma etching, to use a plasma species of different gases to selectively remove different materials. Different gases will remove different materials, and then you can go through the structure layer by layer using any one of those techniques or a combination of all those techniques to be able to do that. Once you've exposed a layer, you then have to somehow image that layer, get a view of the entire structure, image that layer, and hopefully image the contacts between the layers as well as the actual layers themselves, to be able to reconstruct a sort of three-dimensional map of what you have in each circuit. And then you've got to go through that somehow to identify what is actually there. Seeing the structures is one thing, knowing what the structures are and identifying what they do is in many ways the most difficult problem of this whole exercise. So knowing what's there from a functional point of view is a critical thing. Now, I know there was some, at least some training yesterday where there was one group who were showing some very good software for being able to do this sort of thing. It's a difficult problem, but it's one that is now being solved. Okay, so stripping back the layers, if you were to do this, you could go through a layer. This is actually going from the reverse direction. Normally, as you strip back, you look at the top layers first as you go through, and you go down through the stack. This is what you might see right down at the bottom. Polysilicon right above the silicon layer itself. So the silicon are these sort of gaps in the middle there. There's polysilicon layers as part of the gate structures you'll find in a logic area on a chip. And as you go up through there, you have different layers going through here. So you've got some power lines and ground lines here and lots of different circuit elements in between. What they are at the moment isn't exactly obvious. But you can go through this and identify what some of these things are to find out what kind of structures they are. At the moment, however, these are isolated structures, could be flip-flops or something like that, but not connected to each other. And as you go through the stack, this is rather darker than I expected, by the way, so I'm sorry about the image quality here. I thought it would come out a little brighter than that, but there's another metal layer above there. And each time you come up, there's another metal layer. And you can see the density of metal layers you get on and this is not a complex circuit, this is a relatively ordinary circuit. The density of the metal layers which are the connections between the different elements of that circuit, and how you try to sort of work out which ones are connected to what and where they go and things like that. It's a hard and difficult problem requiring some very good experience, some knowledge of what's going on there, and some good software to be able to recognize what these things are, because at some point, and certainly at this point, it gets beyond what a normal human being can work out in their own head. That's a map of where the signals are going. Hard. Go up, there's more metal layers to connect these things in different directions. And all the way up, I think that's the top layer there. And on a properly hardened circuit, you start to get to the next level of problem, which is right at the very top, which are the secure shields that are protecting all that circuitry underneath from your attack using something like focused ion beam system. So you have the circuitry underneath, which you have to try and understand what it's doing, how it's working. And even if you get to the point, if you know where things are and how things work, you still have the final problem of getting through a top shield, which is designed to stop you from getting at the circuit underneath. And in something like this, I know it's hard to really see what it is, but if you see here, it's some sort of wiggly lines, the serpentine lines going all over the circuit. And if you short circuit two of those lines together, there's a good chance the circuit will detect it and say, I'm not going to work anymore. And if you cut a line, it detects it and it says, I'm not going to work anymore. So you're stuck in this thing unless you find some way of bypassing this secure shield. So how can you do that? First thing is to, first of all, consider a relatively easy case of a small single area of that circuit. Let's just say you want to just get a single point in. Let's, an example might be if you want to probe the output of a random number generator. Single line you might need to probe in that. And you may know exactly where on the circuit you need to go from the mapping that you had done previously. And somehow you can relate that to some point on the circuit. So for example, this is difficult to see, but there is a circuit line going through underneath here, under there, and it follows through. You're not actually looking at the circuit line in this actual image, though, because what you have is a circuit line that you can see the effect of, but it's underneath a layer of dielectric insulating it from anything above. So we'd like to try to do something about that. But we have here, for example, a line that comes down from the top, follows round, all the way around here, up here, up here, and up here, and up here. It's a single line, and if we connect from there to there, we can create a bypass that will effectively eliminate all this little bit of circuitry underneath it. Very local area, but it could be useful if it's just above the area that you're wanting to do something in. Perhaps put down that probe pad or something like that. How can you do that? How can you remove that part of the circuit? The first thing is you can use your focused ion beam to dig through the dielectric above the circuit tracks and deposit a new piece of circuit, short-circuiting that loop of the shield. You've gone through, made two little holes above the circuit track, and just deposited a new track, short-circuiting that out completely. You're not short-circuiting two separate tracks, you're short-circuiting the same track, so you're just removing the effect of that loop in the middle. The next thing is you expose the whole of that extra bit of loop that you have using a dielectric etch, such as the xenon difluoride gas with the ion beam. And then you can remove the metal that you've just exposed. So now you have created a hole in that shield in an area such as this that allows you to get down below that and do whatever you need to do to get to the circuit. However, that's just one little area. It's relatively easy to do that, but it's just one little area. You'd like to do much larger areas of the whole shield which covers the entire chip if you can. And it's a little bit more of a difficult and complex problem to remove the entire shield. So how might you do something like that? The first thing is you would like to be able to recognize where the entire circuits of that shield are. And in this case, I've put the circuit not into the focused ion beam, or at least not using the focused ion beam, but in this case using the electron microscope. And if you use an electron microscope and you turn the voltage up to its maximum, 30 kilovolts normally, and you look at the circuit, then some things shine out at you. And these things which are shining out at you are the connections to the layer below. I'm sure that some of you know exactly what those things are. Any answers? Those are the tungsten plugs going down to the layers below. Why do they shine out? And it's because you're using a specific mode of the electron microscope called backscattered electron mode, which looks at electrons not returned to your detector from the bulk of the atom that you're looking at, but electrons which hit the nucleus of the atom and are bounced back in what you call a backscatter event. And since they're hitting the nucleus of the atom, the number coming back depends entirely on the mass of the atom. It's hitting something big and heavy, like a tungsten atom in this case, and therefore more of them get bounced back and you can see them much more clearly. So in something like backscattered electron mode, you can start to see specific parts of the circuit that you wouldn't see if you were using normal secondary electron mode in an electron microscope. Now we can see the ends of those tracks. And in fact, in this case, if you short circuit these two together and short circuit those two together, you can eliminate whole circuits in that shield. So if I go in and cut where those are the two tungsten plugs just underneath there, two two plugs going in parallel down. If you cut that part of the circuit away, you can cut that circuit out, and you cut it there, and you cut it in the other place, and you've now stopped that circuit from contacting anything underneath it. And now look what's happened in the circuit lines. You can see there's two different shades of the track in that circuit. What's happening here? This is an effect we call voltage contrast. So when the electrons, or ions if you're using a focused ion beam to do it, hit a track, if that track is disconnected by cutting it from anywhere else, it is not connected to ground, and it can float up to any potential, any voltage that the ion beam or electron beam is imparting to it. And in this case, if it charges up positively, then what will happen is that the electrons which would like to escape from there can't escape from there. They get sucked back into that area, and the whole thing appears dark. So now you can identify exactly where your circuits are by using techniques like this voltage contrast technique, and identify where the contacts are by using techniques such as backscattered electron imaging. This is all to do with how you understand how your microscopy works to find out what's going on in a circuit. When you know how these tools work well, you can use all their potential, all their ability to give you the information you need to get into that circuit and hack it. Once you've done that, you can make these short circuits, which will then short circuit where that part of that circuit track begins, where it ends, short circuits it, and you can remove very large areas of that circuit. And in this particular case, there were 16 separate circuits in the shield going around. You find the 16 different track ends and beginnings, short circuit them, and you can effectively remove the entire shield from that circuit. Another way of doing it on this is another type of shield where you have multiple shield lines going up and down. And in fact, they would go up to the top, across, down, across, up, like that. But you don't know exactly where the lines are, because the way that the order of those lines gets randomized. Line number 1 here could end up anywhere in the second column of tracks coming down. So you can't just guess which circuits are the beginning or which are the ends of those circuits to put them together. So you can use some information again from the same techniques, such as looking at those little dots there, which are the backscattered electron images that you have here. I guess you notice it's slightly fuzzier, and in that case it's not, it's just a slightly deeper circuit, but we can still see exactly where those the tungsten plugs are going down there. But we still want to find out exactly where that circuit is and how we can begin to bypass areas of that circuit. So one way of being able to do that is that we can start opening up that circuit using a focused ion beam. The first thing is you just expose the first column of 16 lines, which are those 16 different circuits, and you expose them so you can see the metal. That's the bright areas there are the exposed tracks. Underneath that, closer to where the plugs that actually are going down to the deeper part of the circuit, the sensor part of the circuit, you cut those tracks completely. You mill down to the tracks and you keep going and you cut them completely. If you were to power up the circuit now, it would detect that all circuit lines are broken and there's been a breach, and it will shut things down. But you don't power up the chip at the moment. As far as it's concerned, it's still asleep. Next thing you can do, expose those lines, cut the tracks. is you go to the next 16 lines across. So the circuit comes up from the depths of the logic down here somewhere. The tracks come up, and they're cut here, but they come up again further, and they go to these randomizing sort of lines going across, come and down the next 16 lines of the circuit. So you have 16 lines going up, coming across, 16 lines going down, going along all the way across the entire circuit. If we now take the second column here of thing and cut one of the tracks, what do we see? At this point, this particular track that we've exposed here goes dark. Again, that's because of the voltage contrast effect. So we know which lines now are connected to the other ones in the different columns. And all we need to do now is to go down through at the bottom there and make a connection between that line there and the first line of the second column. And we've repaired that particular part of the track. And we can do that again for a second one. We can cut the second line here. We find that it actually comes from here and make a second repair. And do that for all of the lines, which now makes the entire circuit above here completely redundant. And we can remove it completely to get to everything underneath that circuit. Once you've done that, you can do other things such as putting down probe pads. I'm not quite sure how that went dark there just now. But you can put... Sorry. Here's a bus exposed in there. In this case, it's a 32-bit bus, which is quite hard to probe things on. And up here, you've got probe pads put down, contacting onto some of those lines of the bus. There are only 8 down there because I can only probe 8 lines at a time. It's just don't have the tool to be able to do more than 8 on a standard probe station. But you can effectively put more probes down and then probe them separately as you need to do that. And it looks a bit like a graveyard because of all the crosses in there. And this chip is a bit of a graveyard, I believe, but that's the way that it works out like that. Crosses are good because you can get your probe needles right into the corners of the crosses without them skidding away, and makes a good contact for these things. Just to turn things on its head again, and almost literally turning things on its head, because the next topic is going to be how you can come in to a circuit from the back. Because if that shield is too hard to get through, and some of the shields are extremely hard to get through, you might want to consider that you can come in through the back of a circuit. It itself is quite difficult. The first thing is you've got to get through a very thick layer of silicon. Now, when I say thick, I'm meaning something from 200 up to 400, maybe 100 up to 400 or 500 microns thick. That may not sound thick to many people, but to me that's an incredibly thick layer to get through compared with the stuff on the surface. And you can see that you've got, from the back surface of a chip here, you've got this really deep hole to get down into the circuit below. So you don't choose this technique lightly. You do it when you have to, and in some cases you do have to. The case is, for example, if you have a really difficult shield on top to get through, or if the chip has multiple ball bonds, if you're talking about a sort of big processor for a computer or something like that, they've all got ball bonds and you can't really get in from the surface because of that. You will then have to use some technique like this to get into it. And coming into that can be difficult. Your first help is that you can see through the silicon if you have your infrared camera. You can begin to see some of the tracks there. The problem is that you don't have much resolution on that. Infrared beam has maybe a resolution of about a micron, but your fine tracks are much, much smaller than that, so you're only looking at you're only looking at the large features of a chip to be able to find out where you're going. So you're not going to be able to use this to get to the actual tracks you're wanting. But it can get you to the area, and it can get you close to what you're wanting to find. And, of course, to get further points where you can do better alignment. You still need to have your reverse engineered layout for some of these things. And yeah, you still need to have something, and you're not going to have the GDS2 layout from a manufacturer to help you for these things. So the first thing is you start digging in the circuit. You have to go down. An ion beam is relatively it's designed for very small work. It's designed for coming down in areas that are like a micron or even sub-micron level, sometimes a tenth of a micron or something like that. Here you're digging out a whole trench which could be hundreds of microns across and going down hundreds of microns. So it can take some time. And the big difficulty is not keeping digging, but knowing when to stop. Because just at the bottom of that track, just at the bottom of that hole, just before you hit the circuit and destroy it, you've got to spot where the wells are. These are the implantation wells, the Endwells of a circuit that tell you that you're just about at the circuit itself. In this case, you can hit those wells and you'll be okay, but if you go through another micron or two, you completely destroyed your circuit. So you're going to be milling on there maybe for an hour, but you've got to have your finger on that trigger because you've got to stop it within a couple of seconds before it goes too fast and too far. So you find your circuit, and the Endwells become you have to stop digging immediately, and then you have to find alignment points between those active layers to be able to see where you're going. And your problem, again, is always that you don't have the layout which gives you the active layers. You have a layout which you maybe reverse engineered. You know where the metal layers are, but you don't really have the layout which contains the Endwell information as well. So you've got an additional difficulty over many of the legitimate people who are going into sort of rewire a circuit for the manufacturer. So it's always quite difficult, but you can go in there, you can cut tracks again, down at the bottom in there, and do various things. So here's one where you can sort of deposit some tracks and such things. When you get in there, you can do that kind of very, very fine, detailed work within that hole. And maybe you're going to cut some tracks, maybe you're going to deposit some things. Trying to probe down those holes is very difficult, but there's always things you can do from the backside that make these things possible to get into and do those really hard hacks and tests of security on some of these chips. Right, well that's it then. Thank you very much indeed. Okay.
We have time for 2 questions, in case the audience has any.
Thanks for the interesting talk. So I had a question about the identifying the routing of the wires on the active shield. So is it possible to just measure the pattern on the wire to detect which one is connected to which point instead of going through the FIB?
It's kind of possible to do some of these things. So if you have an image of the entire layer, you can see where these things are. But these are very, very long tracks. You imagine that you've got a circuit line which is maybe, I think in some of these cases maybe a quarter of a micron wide. They're big compared with some of the features underneath. But they're still a quarter of a micron wide. And the circuit itself may be several millimeters in size. So you've got thousands of... you've got an awful lot of track to sort of follow. And I've never been very successful in following it by eye. So you could follow it by some sort of software technique to do that. You try to do it. I've always just found it so much easier to use techniques such as voltage contrast to highlight one circuit compared with another and to do it like that. It is a sort of certain way of doing it. But following it by line, is a possibility. It's just tedious and prone to mistakes because they're so long compared with all the sort of meandering that you have to follow.
Are there any shields that monitor the resistance of the track instead of just monitoring if it's connected or not connected?
This has been a topic that has been thought about for a long time, and a lot of security people would love to be able to do that, and it could potentially work. What you're fighting against here is digital designers hate anything to do with analog circuits. They really, really hate it. And so they will say, no, it can't be done. What they really mean is it can be done if you get a good analog engineer, and a lot of these companies don't have good analog engineers, and they don't want to do it. Too prone to, the sort of errors. What happens if when the resistance changes because you've gone to a different temperature or in a, magnetic field or something like that? It makes the circuit far more difficult to design. And it's very prone to error. So designers will say, no, we can't do it. And they really mean, I don't want to do it.
That's usually what it is. Have you ever seen shields? So have you ever seen shields around in-package constructions?
If you mean inside the actual chip package itself, there have been attempts to do that. There was a few years ago, Seashell, I think it was called, meant to make it difficult to get into the package itself. Generally, they've always been got around. I mean, people can find ways of getting around these things by different techniques. And so they've never been really they've never really been used simply because the cost has been more than the manufacturers have been willing to accept for the level of extra security you get for it. So I'm not sure about that. There are other packages that go around systems. So, for example, if you have a payment terminal, they have shields that go around the system, which again protect these things, but the people accept the cost of that because that's part of the cost of doing business in that field. So, but within a chip, it's not very common. Within a chip package, it's not very common. And I don't know anybody actually does it. Okay.
Yeah.
Well, thank you again very much.
Thank you, John.
Very much.